Many thanks to Florence for this interesting and insightful presentation, and also thanks to Anna and Tarek for chairing this session. The aim of this presentation is to introduce a new CIBSE technical memorandum, TM61, on operational performance of buildings, and briefly explain the background to this TM, and indeed a series of technical memoranda that we published with CIBSE a few months ago, TM61 to 64. So it's really about the aims and scope of TM61 as the core document, and then we had a number of spin-offs to do with very specific and detailed protocols. TM62 on best method and best practices of conveying building user surveys. TM63, a protocol for measurement and verification of building energy performance in use. And TM64 to identify the key sources for pollution in terms of indoor air quality, key sources of contamination, pollutants, and the best way of mitigating these sources to achieve good indoor air quality. But TM61 is the core document which deals with the intricate relation between energy and indoor environmental quality. So adopts a holistic approach to building performance, taking energy as the input to environmental systems within a building and indoor environmental quality as the output. These TMs were developed based on several research projects at UCL IEDE and also our platform grant, Complex Built Environment Systems platform grant, and later Built Environment Systems Thinking. And notably, the total performance of low carbon buildings in China and the UK, the TOP project, the EPSRC funded project that helped us to define several case studies for CIBSE TM61. So all case studies are based on the TOP project. A bit of background. There are several initiatives now in the industry and indeed frameworks and tools to facilitate nearly zero energy buildings and net zero carbon performance. Notably, RABA 2030 Climate Challenge actually was launched last year with a view to and with an ambition to achieve net zero carbon performance by 2030. Plenty of architectural practices and other companies in the construction sector actually have already signed up to RABA 2030 Climate Challenge. So it's really promising. We have several other initiatives. Design for Performance is a good example. Again, we actually had the launch of Neighbours in the UK only last week. So there are attempts to facilitate this transition to net zero carbon buildings, which is great. Very much focused on energy efficiency and carbon emissions associated with energy use. There is a potential unintended consequence here that we have seen time and again in several buildings. And that's where we started thinking of Technical Memorandum 61. So that was how the idea was emerged based on our past projects. How we can make sure that we strike the right balance between energy performance and indoor environmental quality, as some of the measures to improve energy efficiency might have knock-on effect on indoor environmental quality. So this balance is quite important. To illustrate the point, I would like to provide you with one example based on TM61. There are several other examples in this TM in case study chapters, but I think this is a good example just to show the extent of the problem and what we mean by this intricate relation between energy performance and indoor environmental quality. This is a residential development in East London, a couple of apartment blocks completed back in 2015. As you can see, very airtight, low air permeability, and for that reason, they are mechanically ventilated. So they have an MVHR system, mechanical ventilation with heat recovery, to make sure adequate background fresh air is always provided to apartments, especially in winter, when the working assumption is people don't rely on operable windows. So it should be mechanically ventilated. Now, generally speaking, in dwellings and residential buildings, air change rates are lower than non-domestic buildings. And when you have such a airtight building with such low air permeability, lower than 3 cubic meter per square meter per hour at 50 Pascal pressure difference, What happens is, in terms of air quality, the indoor sources of pollutions become more relevant. So in a non-domestic building, say in an office and a hospital building, in which you have higher air exchange between outdoor and indoor, high ACH, you're probably more worried about outdoor sources of pollution. In urban areas, for example, when you have traffic congestion, could be PM 2.5, NO2, and so on and so forth, primarily driven by outdoor sources. But when you have low ACH, like this example, indoor sources might also be problematic. So in this project, in addition to monitoring outdoor sources of pollutions, we deployed adsorbent passive tubes to measure the average concentration levels of various pollutants, some of them driven by outdoor sources, most of them driven by indoor sources, construction material, furniture, and so on and so forth. So you can see here the outcome of this investigation in a couple of apartments. You can see the concentration levels of various VOCs, volatile organic compounds, compared against best practice exposure limit values internationally, as identified by International Energy Agency Annex 68 program, but also the guideline exposure limit values issued by Public Health England last year. So both the UK sources and international sources in terms of best practice and guideline exposure limit values. And as you can see, in terms of benzene or formaldehyde, we have witnessed concentration levels significantly higher than these guideline limits. Now, benzene is primarily, again, driven by outdoor sources, is more to do with filtration within the MVHR. I don't touch on that in this presentation. But formaldehyde is a very interesting case because this is primarily driven by indoor sources. Could be construction material, laminate flooring, a kitchen cabinet, use of medium density fiberboards, and so on and so forth. And of course, flatback furniture, manufactured wood like IKEA furniture, or indeed flatback furniture from other suppliers. So this seemed to be a problem, and it was not confined to these two apartments. This is just to illustrate the point. We monitored several other apartments in these blocks, but also we have the international evidence, again, emerging from our involvement in IEA Annex 68. This is the outcome of subtask 1 of that research program, and you can see concentration levels of various pollutants in low energy buildings. And the proxy used to define low energy buildings was basically year of construction. So in the EU, for example, inception of the Energy Performance of Buildings Directive in the member states was a good proxy to identify low energy from non-low energy buildings. So that's how we define the low energy buildings. And then based on several studies carried out on these buildings, metadata analysis was done to identify the key pollutants in which you may have concentration levels higher than exposure limit values. So as you can see here, benzene and formaldehyde have concentration levels higher than exposure limit values. Again, best practice ELV. And you might have episodes of high concentration levels in terms of other pollutants, but these two pollutants are also quite problematic, as you can see. And again, here you can see the full picture, both in terms of indoor sources and outdoor sources of pollution. But the point is, the problem that we witnessed in terms of formaldehyde was not limited to one case study. There is more evidence, international evidence, to support the fact that in low energy buildings, in airtight dwellings, we tend to see this problem. And this was by the way low energy residential buildings. So we are talking about dwellings here. And again, more international evidence. This was news a couple of years ago. And here in this example, we were dealing with concentration levels above 100 microgram per cubic meter. So significantly higher, factor of 10 higher than best practice exposure limit value. So this tells us problems around the labeling of construction material, emission factors, quality control, and indeed quality assurance issues in the construction industry, which becomes more problematic when you don't have adequate ventilation, or you don't have adequate is probably not the best word. You don't have sufficient ventilation to overcome the impact of high emission rates in terms of formaldehyde, but also other VOCs potentially. Now, generally speaking, when you're dealing with internal sources of pollution, there are two strategies to control pollution. Best one is the so-called source control measures, so using low impact or low VOC material, and then you would be able to supplement that strategy by enhanced ventilation. So you would be able to increase the ventilation rate, in this case in the MVHR system, for example. But of course, enhanced ventilation brings the problem of excessive energy use. So in this case, we developed a model and we figured out if we want to overcome the problem in terms of formaldehyde concentration levels and bring the levels down to best practice ELV, we really need, given the existing material and furniture, which was out of our control, we are dealing with an existing building, we had to triple the rate of ventilation, which will have a significant knock-on effect on energy use. So it's really not good practice. We really need to focus on source control measures. But this tells us the problems that we are basically seeing in these so-called low energy buildings. And basically we need to focus on development of labeling schemes and also identification of key sources for indoor pollution to make sure, in addition to energy efficiency, indoor air quality is also acceptable, and we strike the right balance between these performance metrics. So that was only one example. Again, we have several more examples in this technical memorandum. But the point is that improvements in energy efficiency might bring unintended consequences and negative feedback loops in terms of indoor environmental quality. Not necessarily in terms of all measures, but sometimes there are conflicts between these measures. And it's quite important to be aware of it, to identify these conflictive measures and try to mitigate the risks. And that was the main driver behind the development of technical memorandum. Now, a more recent example from the other end, so measures that could improve indoor environmental quality also can have knock-on effects in terms of energy efficiency. Speaking of the pandemic, the problem that we are now facing, now there's increasingly an acknowledgement of the risk of airborne transmission of virus. Is not the direct route, of course. There's acknowledgement that the direct route in terms of sneezing, coughing, and direct contact at short distance is the dominant route for transmission, but airborne transmission is now understood also to be an important mechanism that we really need to deal with. And indeed, airborne transmission of viruses is well known, is a well-known phenomenon in design of ventilation system. It's nothing new. But if you look at different guidelines available in the industry from professional bodies, but also journal articles and different research projects carried out in this domain. It's interesting that most good and best practice measures and key principles involve measures that can lead to increase in energy use. So I have included some of the key measures here. So increase ventilation rates, disable demand control ventilation, again, to maximize the ventilation, both in terms of the rates of fresh air, but also the duration of ventilation, so extend the schedule of ventilation. If you have recirculation, good practice is to close the recirculation dampers and opt for full fresh air, assuming, of course, in terms of heating and cooling, we have adequate means to make sure that the thermal comfort conditions are maintained within the building. If not, if it's inevitable to use recirculation, really we have to opt for advanced filtration like HEPA filtration, which again will increase pressure drop and can have a knock-on effect in terms of fan energy use, so will increase the energy use. And also when you're dealing with heat recovery technologies in a country like the UK, turn off or bypass thermal vents, because in this specific heat recovery mechanism, there's a risk of cross-contamination between extract and supply air. And I also touched on filtration level, again, improving filtration. So all these measures can increase energy use. So it's not one way. If you want to improve indoor environmental quality, there might be penalties in terms of energy use. So the balance is quite important. Now, in the context of COVID-19, we are dealing hopefully with a short-term phenomenon, but already designers are talking about long-term impact of basically COVID-19 in terms of key lessons learned for future design. So I'm sure in future people will be more focused on ventilation systems and ventilation strategies and mitigation measures to be able to tackle problems down the line in terms of transmission of viruses in future. So that was my second example. And with that background information, just want to present the structure of this technical memorandum. So we focus in terms of the theoretical principles. We focus on energy performance and indoor environmental quality in 2 chapters following the same structure and method in terms of identifying the key causes of underperformance, both in terms of energy and IQ. And then we have 4 case studies in the sectors that put together constitute a large cross-section of non-domestic buildings and large residential buildings in the UK. So offices, schools, hospitals, and apartment blocks. We presented a very detailed study of energy performance and indoor environmental quality in these case studies. This led to development of some tools and protocols I mentioned before, TM62 on basically occupant satisfaction surveys, TM63 measurement and verification of performance in use, and TM64 focus on emission sources and mitigation measures. And we try to treat both energy and IQ holistically and longitudinally. What I mean by that, and this is probably a good illustration to show the point in terms of energy performance, but we can extend it to IQ and indeed even occupant satisfaction in terms of expectations and design stage, and then the actual performance, is you would be able to depict the evolution of performance at design stage, early design to construction, and then post-occupancy, and follow that. So in this case, we have a target. It could be regulatory target. It could be a client target. If we outperform that, we are in the green area. Usually that's the case at design stage, the so-called design optimism. So we try our best to achieve basically design targets. But then when it comes to construction, and specifically in operation, things tend to go out of control and you might end up having a problem of performance gap. So it's quite important to try and bring down that curve from this point to this so that we manage to achieve our energy performance targets or indeed carbon emissions target. This is for energy, but we can extend it to indoor environmental quality. So this holistic and longitudinal view is important, but also it's quite important to focus on this stage, and we develop protocols to use building performance simulation and calibration to identify key issues in buildings and then try to tackle those issues. And we distinguish between different stages of the project. Florence touched on RABA stages, different RABA stages, focusing on design, construction, commissioning and handover, and then operation. And what are the key risks throughout building procurement at each stage, both in terms of energy, but also indoor environmental quality, and how we can tackle these, and what are the endemic issues, and what are the mitigation measures. So that's the focus in our theoretical chapters. And then we move on to our case studies. And this is one example trying to move beyond the energy performance calculations carried out at design stage to more bespoke calculations, the so-called energy budgets in a case study that was subjected to performance contracting, and use a protocol that we designed in TM63 to derive a robust baseline for performance, reflecting the actual operational settings and functionality of the building with the design intent in terms of technical systems. So you can see different definitions of the so-called performance gap, depending on the reference point that you choose. And we believe that the operational baseline derived from TM63 is probably a good one for building performance optimization and for building diagnostics. It was not limited to energy, of course. Again, in terms of indoor environmental quality, I touched on formaldehyde and indoor sources of pollution before. This is just to show that for each case study, we also measure thermal comfort conditions, various pollutants, outdoor source pollutants, indoor source pollutants, and so on and so forth. In 4 case studies, exemplar buildings in many ways. There's always room for improvement, of course. But we had, for example, Keynsham Civic Center that won CIBSE Performance Awards a few years ago. This is the building that was subjected to performance contracting. Brentwood School won Sterling Prize Award back in 2015, and also a hospital in Bristol and the apartment blocks in East London, which is a very large regeneration scheme. So lessons learned from this project and from these blocks are applicable to plenty other new residential developments on that site. Last but not least, we also engaged several stakeholders in these case studies to try and understand the interplay between different actors, clients, architects, building service engineers, contractors, subcontractors, the so-called soft factors, and the contractual arrangements and the leverage points that could basically optimize performance using a participatory system dynamics approach and different feedback loops. As you can see, these emerge from the workshops and discussions with stakeholders. And then we try to convert this rather complex picture to a set of simple and, if you like, user-friendly recommendations and guidelines as to what measures could be used within a given contract to try and tackle the issues with underperformance in energy and indoor environmental quality performance. So you can see some examples here, but it's not limited to this table, covering different phases, design, construction, operation, but also at different levels, dealing with ambitions, paradigms, mindsets within organizations, coming down to goals, rules, incentives, information flows within a project, how these information flows really need to be designed, and the structure of the project. So this was the annex, and this is a summary of this technical memorandum. If you are interested in the subject and if you want to learn more, please refer to technical memorandum on CIBSE Knowledge Portal 61, and also 62 to 64 deal with specific protocols as I discussed before. Thank you very much for your attention.